Whaley. I'm joined by my partners Hadi Ashamari, Corey Bova, Caitlin, and Presley. Today we're going to talk about thermal injection, more specifically cyclic steam injection.
So cyclic steam injection has become a common process of heavy crude oil extraction, and this method falls under the thermal oil reservoir simulation approaches, and is considered an enhanced form of oil recovery, which is our subject for this course.
So I'm going to talk about the chemical analysis for thermal injection, specifically some of the new chemicals that are being used around the world today.
And whether you're an oil company or your local grocery store down the street, the bottom line almost always comes down to economics. So I'll be looking at some of those factors that go into those economic decisions.
I'm going to cover the other methods of thermal injection.
And then we'll have some time at the end for questions if you guys have any.
As a method of thermal recovery, the process of cyclic steam injection involves injecting a well with steam, after which it uses subjected subsequent production. Specifically, I'll discuss all three stages, each one, in next slides. So the first stage is steam injection. Steam injection into a well is controlled with a temperature range of 300 degrees Celsius and 340 degrees Celsius. It may take up to weeks or even months depending on how prepared the production capacity is, and it's always done with high temperature and high pressure. And here's a figure shows the high steam injection. And as you guys can see, here is the steaming injection system, include the pipeline, thermal wellhead, steam injection string, and also a steam generator. And this picture shows the steam generator if you guys didn't see before. Next, second stage, which is soak phase. Strain the well is necessary to maintain the right pressure and temperature during the period of soaking the crude oil. In order to optimize the soaking process, the well should be left tight for at least 5 days. And that's important to provide effective time for steam flooding to improve economic efficiency in oil extraction. The third and last stage is oil production phase. Production of oil begins when the well is unsealed. Hot oil will puff out from the well. Due to build-up pressure and heat connection, hot oil can be easily bumped out for refining. This process is repeated as many times as possible, especially when the oil production is viable. Here is a figure shows all the three stages, which are steam injection, soaking phase, oil production phase. And I will talk more about this picture. As you guys can see, it shows the producing ability. For example, the red area has the lowest producing ability, and the blue area here has the highest. So we understand that when we go from inside to outside, the producing ability increasing. The last thing is condition applicable in cyclic steam injection. There are selection standards or guidelines that should we follow to ensure successful cyclic steam injection. These standards define the depth, porosity, permeability, oil saturation, and viscosity standards. And this table shows the successful cyclic steam injection. We need to make it at least or close to these numbers or these selection standards.
So I'm going to talk about the chemical analysis for a thermal injection project, and obviously the most important things that we're looking for in a thermal injection project is increasing recovery as much as possible. So there's always going to be new studies on what chemicals are going to increase displacement efficiency, how you can lower costs in that aspect, and how you can be more environmentally friendly as a company. The biggest obstacles for thermal injection are adverse interfacial properties, including wettability and interfacial tension. And these are properties that exists between the oil water and the steam rock systems, and they're something that the chemical additives that are being implemented is trying to overcome. A lot of the heavy oil reservoirs where thermal injection is necessary, those reservoirs are oil wet, and that's a problem. Obviously, it makes the oil harder to produce, and a lot of the focus is how you can change that wettability in the reservoir, and the process of doing so by thermal or chemical methods is known as wettability alteration. These next couple charts came from a study by 2 students from University of Alberta on new generation chemicals in the thermal injection world. And this is an example of some of the chemicals they use to test for contact angles in solution, in comparison to tap water. 2 of the chemicals I'm going to discuss are the BMMIMBF4 chemical, which is an ionic liquid, and the C12 tab chemical, which is a cationic surfactant. This is an example, again, this was just done on calcite surface, but this is how those contact angles shift as the temperature heats up. And this is an illustration, as you can see, of the oil droplets at the surface at different temperatures. The next thing that they look for is interfacial tension in the reservoir, and decreasing the interfacial tension has been shown to greatly increase the displacement efficiency of the injected fluid. Laboratory core flooding tests have shown that reducing interfacial tension can improve displacement in various wettability conditions, either oil wet or water wet. And some of the factors that affect the interfacial tension are pressure, temperature, oil composition, and the chemical additives present. Historically, adding aqueous solutions has kind of been the idea and the main mechanism for how you're going to lower interfacial tension. Something that we've talked about before is surfactants. Everybody is fairly familiar with that, and that's kind of just like a soapy substance that helps reduce that interfacial tension. Some of the new generation chemicals discussed in the study were biodiesel. That was originally proposed as an environmentally friendly alternative to surfactants, but through their testing they found out that it's a great supplement to a standard surfactant for lowering the interfacial tension. The ionic liquid, BMMIMBF4, I'm not even going to try and pronounce that because I'm going to screw it up. They noticed in their testing that that was a thermally stable compound, but it increased the interfacial tension, but also increased the production in their core flooding tests, and that's mostly attributed to the wettability alteration capability of the compound. And the last one that I'm going to discuss is the cationic surfactant, C12 tab. And in their testing in the lab, they saw that that reduces both the contact angle of the oil droplets in solution and the interfacial tension. The only issue with that is that it was done at a low temperature in a lab, and that compound is not really useful in an actual thermal injection situation because of its thermal stability.
Okay, there's a lot of metrics in the economic world that you can look at. Today I'm going to focus on the few that have a large impact on the viability of a tertiary recovery method. So first and most importantly is to look at the price. The standard is West Texas Intermediate, which as of today, a barrel of oil is sitting around $52, which is okay but not great. When oil is good, you want to get as much of it as you can. So this is when your tertiary recovery mechanisms are recommended. But when it's not, more production is not always better. You might spend more money recovering that oil than it's worth. So that's the first step you need to look at. The second, I believe, second most important is your NPV, which is your net present value. NPV is a balance of your expenditures and your inflows into cash flow to get you your revenue with time factored in. Because $5 million today is not the same as $5 million 10 years from now. So when you're investing in a project, you need to look at when you're getting your money and how much of it there will be at the end. And you have to look at before and after taxes, because before you take into account taxes, it might look viable, but depending on where you are, a high tax rate could be as 30, 40% in some scenarios, which would make a project no longer viable. Another metric to look at is maximum capital expenditure. And this affects smaller mom and pop companies more than it would a large company like Chevron, who has billions of dollars to throw around. But for a small company, they can't stretch themselves too thin because you want to be diversified and you can't invest too much in one particular project. So if you don't have enough money to begin with, or you're stretching yourself too thin, you can't engage in a project even though if it looks viable. Also, it's important to look at royalties. An image here shows from the Canadian government their two auctions they give oil companies. There's two sliding scales, a gross revenue scale and a net revenue scale. Now, this is a little bit of a gamble for companies on what they select, which is up to them. When you go by gross revenue, your royalty rates go off your total revenue. This is your gross revenue. So it doesn't take into account your cost for labor, your cost for materials. So if you end up having zero net revenue, you're still paying royalties, which is why it's a gamble, but they're lower rates, which is how you can save some money there. The safer option is your net revenue sliding scale, where you only get royalties taken out of your net revenue at the end of the project, but these rates are a little higher, which is why some companies don't like this option. And this takes me to my next point of working interest. And simply put, working interest is whose pockets the money is coming out of to fund a project. A lot of these large projects are joint ventures, so a lot of times you'll see a 50-50 split between companies or a 60-40 of who's going to pay for it. And then your net revenue interest is then who's collecting that money. A lot of times the landowners will get 20%, and then the company will get 80%, or whatever deal they work out. Then it's also important to look at the environmental aspect when you're considering economics, because squeezing every penny out of a situation isn't always great if it makes you look bad to the public, which in 2018 it's very important for the oil and gas industry to fight for a better positive image. So the first thing to look at is your steam to oil ratio. This is simply how many barrels of steam you inject to how many barrels of oil you get out of that. California requirements are 0.5 to 1, which is one of the main usage of cyclic steam injection. This is very strict rules, seeing as a typical SOR is 3 to 8. But so even though some California instances you're still economic, you must shut down your tertiary recovery mechanism or method because of environmental regulations. It's also important to look at water. Not only the cost to inject water, but the cost to clean it once you get it back, which is kind of a backdoor cost there. Nowadays, even if you're using dirty water to begin with or slick water, you're seeing 50 cents to 80 cents per barrel to clean that up at the end, which adds up when you're injecting massive amounts. And then also your central processing facility, as shown here, has a large carbon footprint, and it takes up a lot of land. So companies are working on minimizing acreage of this, and also maybe finding other ways to power it other than straight natural gas, such as solar power, to cut down the carbon footprint.
So now I'm going to cover the other methods of thermal injection. So we have focused on cyclic steam injection, but there's also 3 other methods of thermal injection. Those being steam flood, also known as steam drive, steam assisted gravity drainage, and fire flood, also known as in situ combustion. So I'm going to first talk about the steam flood. In this form of recovery, steam is constantly injected into your reservoir through the injection well. This is done to heat the heavy oil and to improve the viscosity. A water drive also pushes the oil towards the producing well when the steam condenses into hot water. Next is steam assisted gravity drainage. One well, there's 2 horizontally drilled wells, one above the other, about 5 meters apart as seen in the diagram. In the above well, pressurized steam is injected into the well to heat the oil, making it less viscous. This forces the heavy oil to drain into the bottom well, where it can then be produced. It is mostly used in very heavy oil fields and oil sands, and the recovery rate is about 50% of oil in place. The last method is fire flood. In this method, heat is generated inside the reservoir. Fire burners are used to provide fire burns into the formation in shallow situations. In deep formations, the fire burners are generated by injecting air and other mixtures through the injection well. The hot gases provided by the fire flames reduce viscosity in oil, which forces the heated oil towards the producing well. In some cases, water can also be injected, which turns to steam, creating an additional force to help move the oil. There's three ways to achieve combustion, these being dry forward, wet, and reverse combustion. In dry forward combustion, the fire moves in the same direction as the injected air towards the producing well. Wet combustion is when water is injected behind the fire burn and transformed into steam by the hot rocks that are heated by the fire front. This is also known as a combination of forward combustion and water flooding. Last, in reverse combustion, the fire front moves in the opposite direction to the air being injected, and this recovery rate is about 30 to 40% of the boiling place.
So in conclusion, the process of cyclic steam injection has the three stages, which are the steam injection, soak phase, and oil production phase. And this process has the higher success rate other than the other techniques due to improved swipe efficiency and reduced cost of directional drilling.
So as I said, the most important focus with the chemical analysis for a thermal injection project is how you're going to increase that tertiary recovery, how you might be more environmentally friendly, and how you can lower the overall cost of the project.
We'll quickly glance over our references, and at this time we'll open up for any questions you guys may have.